And we're good. All right, everybody, welcome to lecture whatever this is of whatever this class number is. It's nice to see you all. Let's see here. So today we're going to kind of finish off our discussion of linear systems of equations and then move on to more discussion of linear systems of equations, but using some other approaches. Namely, we're going to introduce the QR factorization and then eigenvalue problems and then SVD, and then finally we're done with matrices. But that's like sort of the first, somewhere between third and a half of this class. As I posted on Piazza, somehow we are ahead of schedule for this course, which is shocking, and probably a lesson for me that I talk too fast. So in the interest of not totally overloading you guys, which is a polite way of me saying that like A, that, and B, I overload myself because then I have to prepare more lectures. But for both of those reasons, today we're going to kind of take it a little more slowly, do the remainder of the lecture we started last time, which is really what was on schedule for today anyway. And then we may finish a little bit early, which is fine because the last couple lectures have gone a bit late. And if that's the case, I'll just hang out and have off-stars, which I'm guessing is more useful for you anyway because your homework is due. Any questions, comments, concerns on that front? That's our, I think, a reasonable plan. Fantastic. And of course, as a reminder, your homework is due. So you should do that. And we forgot to write your short quiz again. I'm sorry. It's really hard running a course for the first time. So Chris is kindly drafting that as we speak. Don't read over his shoulder. But as you saw in the previous quiz, these are not intended to be particularly difficult. They're just intended to make sure you remember the vocabulary words from the week and are keeping track of the course material. And then the last thing, of course, is that homework 2 has been posted. We went ahead and posted it just because it was ready. Like, obviously, you know, you can wait a day or two before you start. I would recommend in homework 2, at the very least, download the starter code and make sure that it runs on your laptop. So if it runs correctly, then what should happen is a window should pop up on your screen, and there should be a 3D armadillo that you can rotate. That's what's in the starter code. So if that doesn't happen, then you should come check with us ASAP. The computer graphics code is famously annoying to get to work on a bunch of student computers. So we're using this polyscope library, which seems to be pretty well. Like, we tested on a Mac and on a PC and in Linux. It seems to be okay, but you know, who knows? Maybe we just had good luck with the 3 computers we tried. So at the very least, make sure that it runs on your machine as the starter code. And then the reality is the code that you're writing is mostly like the back-end numerical part. So I'm actually less worried about that working on everybody's machine and more worried about just the starter code going. Also for that assignment, unfortunately, this always happens when you design classes like this that have like slightly larger assignments. They're never perfectly aligned with the lectures. You should be able to get started with this, but one thing you might want to read ahead about a little bit is this singular value decomposition. To do many of the problems on this homework, it's enough to just know that it exists, which you might want to, like, you know, just like page forward a little bit, or if you remind me, I can post those chapters of the book. Obviously, we'll do it in great detail, but that way you can get a head start, which is what I know you all want to do. Okay, any logistical questions, comments, concerns? Fantastic. Incidentally, on this homework, the extra credit problems are mostly software engineering, which is a very different kind of challenge, but indeed making this one run quickly is an interesting engineering kind of difficulty. The other one, if you're want more of a mathematical challenge, is that a little piece of this homework is going to be to basically work out how to project a matrix onto the orthogonal group. Do a fancy way of, like, for a matrix, find the closest one whose columns are orthonormal. You can work out the same version of our algorithm, but for the special orthogonal group where your matrix has determinant 1. It turns out that projection formula is like 1 letter different from the projection formula you're going to derive on your homework. But to my knowledge, the derivation of it is much more annoying. So just fun fact. Okay, so with that, unless there are any questions, we'll get started with what we're actually planning to do today. Okay. So what have we done so far? So far, we've written a bunch of code that inputs a matrix and maybe a right-hand side, and then outputs like A inverse times B, right? Like solves a linear system of equations. We started there, and then we kind of, so our general purpose algorithm there was Gaussian elimination. And we noticed, and this is going to happen a lot. Like, we start with a problem, then we just start building more and more structure on it, right? So, like, kind of looking at the Gaussian elimination algorithm, we quickly realized that the steps really only depended on the matrix and not on the right-hand side. And that's what allowed us to derive this LU factorization. And then, and the LU factorization is useful for like solving a bunch of instances of the same linear system with different right-hand sides. Right? That's where that often comes up. Then we kind of took a detour and looked at a few examples of where linear systems of equations show up in computational practice. And the thing that we noticed is that they often have nice structure. And so the two of the structures that we discussed, one of them in great detail and one very briefly, were positive definiteness, which tends to come from least squares problems, and sparsity, which tends to come from problems where you like have some kind of a network and variables are talking to each other along the edges. And at least in the case of positive definite matrices, we went in great detail in our previous lecture on an algorithm that is a little more stable and is specialized specifically to that case, which is this Cholesky factorization, which in some sense you can think of as a special case of LU, right, where U happens to be L transpose, right? And that's about where we left off. So now, to kind of bring our discussion of linear systems of equations full circle here, so we now see some places where linear systems of equations show up in real life in computer science. We have convinced ourselves that there are some algorithms for solving them. We haven't derived like the world's fastest algorithms. I mean, there might be other ones out there, but we've derived enough to know that we can do it. Now, the last thing that we should always answer when we're doing good numerical analysis is like, we can solve it, but should we? You know, in other words, like, is our problem well posed to begin with? Or like, can we even sense whether or not we've solved a linear problem to our favorite level of satisfaction? Yeah? And in particular, remember that we sort of have the error that we actually care about and then the error that we can actually measure, right? So again, like as a little bit of review, if we're trying to solve ax equals b, then maybe we have x star is the true solution. And then we have x naught, which is the computed one. Now, in the algorithms we've talked about so far in this class, these are probably pretty close to each other, like within numerical precision. Right? Like the only errors that we're really going to see in Gaussian elimination are just the add, subtracts, and multiplies, but it's like a finite number of steps. Later in this course, we're going to talk about conjugate gradient algorithm. Are we familiar with conjugate gradient? Yeah. Oh, good. I finally found one that you people don't already know. And CG is an example of an iterative algorithm that's going to start with an estimate of x naught and then just iteratively try to make it even better, right? And so that would be a case where like your error is likely to be larger than numerical precision because you might stop it early. And then this discussion is going to be even more critical. Yeah? By the way, even if you're not familiar with conjugate gradient, I'm guessing many of us have heard of gradient descent. Yeah. So for instance, you guys have all missed a totally obvious algorithm for solving ax equals b, which is to do gradient descent on the norm ax minus b. Right? So this is a function that maps, you know, from a vector x like that, right? So a perfectly reasonable algorithm is to take x and then update it by just adding a small or subtracting a small multiple of the gradient of this thing, right? That's actually a totally reasonable algorithm, and there's some argument that it's efficient in some cases. And this is another example where like maybe I do a few steps of that and I want to evaluate how close I am to the solution, then I'm still going to need the machinery we'll talk about today. Does that make sense? So we're going to take like a ginormous detour before we talk about iterative solution of linear system, because we're going to do the kind of general case first, like iterative solvers for nonlinear problems. And then we're going to show that like a special case of those gives some really elegant algorithms for linear stuff that are quite different from what we're doing in class here. Okay? So to put it differently, you know, we get this thing, you know, Gaussian elimination works in theory, but we don't know about floating point precision. And moreover, if somebody just guesses a solution x naught, like we want to know how close it is. And so of course there is, you know, what we want is to bound this quantity, right? Which is like what we would all consider to be the error, right? I guess the 2 norm, not necessarily, but some norm in the difference of these two vectors. But of course, this is not actually a measurable quantity, right? Because it requires knowing x star. And that's like sort of the whole purpose of our algorithm, so it's not really fair game. But what we can measure is maybe ax0 minus ax star, right? Because this is just b, right? And so what we want is that this guy is predictive of that one, right? In other words, that like if the backward error is small, the forward error is small too. Hopefully this story, like if we repeat it enough times, starts to become familiar and boring. That's my goal. Okay? So that's what we're going to do today, is essentially a very careful perturbative analysis here, where we're going to say if I, think about the independent and dependent variables of our computation problem. So in other words, the input and the output, right? So the input is A and B, and the output is X. So we're going to ask the question, if I perturb A and B, how much does X change, right? And that's going to be, if you think about it, sort of related to the ratio between these two notions of error, okay? So that's our goal today. So if you recall from our previous lecture that I rushed through for no good reason because we were ahead of schedule, essentially we took a little bit of a detour because we said, okay, well, for one thing, just from college linear algebra class, we're so used to computing two norms of vectors, but actually there are a lot of norms out there in the universe, and all of them can be used to decide whether a vector is large or small. So we took a bit of a detour to justify that, this is really the set of axioms we care about, right? That we have some notion of length that scales to 0 in a proper fashion, has a triangle inequality. And moreover, specifically for matrices, computing the norm, if we care more about a matrix in terms of thing that acts on vectors, instead of just a pile of numbers, then it might be that we want this kind of subtle definition of a norm called the induced norm of a matrix. Yeah? So as a bit of a review, at the end of the last lecture, we very quickly justified what is the induced 2 norm of a matrix. Do you guys remember? No, so the Frobenius norm is the sum of the squares of the entries of a matrix. It's actually not an induced norm. In fact, if you want a fun theoretical problem, it's to prove that it is not an induced norm, induced by a vector norm. It's kind of a tricky one. Yeah, it's the largest singular value, or if you don't know what that is, then if you take A transpose A, you compute the largest eigenvalue, we showed that the square root of that number is actually the condition number, right? And of course that's tricky because we don't know how to compute singular values in this class, so it's a mildly useless measure so far, right? And in fact, I think most of us would agree that eigenvalue computation is going to be algorithmically somehow more tricky than linear systems. Yeah. Okay. So then that suggests that maybe actually when we're evaluating things like condition number, it might be valuable to write it in terms of norms that we can actually compute. And so two of them come to mind, which is the induced norm for the L1 and the L infinity norm of a vector. And these are actually computable, right? So this, for example, the induced L infinity norm here, if you you have to squint at the indices here to make sure that you agree with me. So remember, this is row and column for I and j. So what is this inner sum here for infinity norm? Make sure you guys are thinking critically when you read these equations. That's right. So remember that here is I is fixed and you're varying j. So it's going across. So this is the max of the sum of the absolute values of any row, right? And fun fact, this thing is a triangle inequality, which is sort of inherited from the fact that it comes from the vector norm for L infinity. Yeah? This has a triangle inequality. So namely, if I take two matrices and I add them together, this thing is upper bounded by the sum of the L infinity norms of the two. It's actually a good little exercise to show that this is true for any induced norm. That if you have this general definition up here, where the double bar just has a triangle inequality. So notice that there's sort of two double bars, the one on the left-hand side and the right-hand side. So the left-hand side is for matrices, on the right is for vectors. So what you can show very easily on your scrap paper, I encourage you to, is that if the one on the right-hand side, the vector norm has a triangle inequality, then the one on the left-hand side does too, the matrix norm. This sort of makes sense, right? Because it's kind of inherited from the other. So for fun, I thought we would derive the L infinity formula real quick, just to give you a bit of a flavor of what that looks like. Incidentally, this is quite similar to one of your homework problems. And I think it's useful also just to whenever you see notation like this, I think it's so important to unroll and just make sure you understand what we're actually saying about life. I think it's really easy in classes like this. It's even worse in algebraic geometry, incidentally, to just write down a bunch of formulas that you agree with and then step back 10 feet and be like, what the heck did I just do? And I think this is a space where you run a large risk of that. So in any event, let's actually derive I chose the second formula because it's slightly easier and I'm lazy. Okay, so in particular, let's say I wanted to compute the induced infinity norm of a matrix A. So what is this thing? Any idea? Well, remember, it is you can write it as follows. So it's the infinity norm of a times x for some vector x, right, over all vectors x whose infinity norm is 1, or I guess really less than or equal to 1. By scaling, equals to 1 is sufficient here. Yeah? Does that make sense? All I did so far is just take the definition of an induced matrix norm and write it out for the infinity case. Okay. But here's the thing. So this is the max over x, right? Remember that the infinity norm is itself a max. Do you see that? Okay. So in particular, this is the max over x and indices I of the absolute value of ax index I, like that, right? Because this is defined to be the L infinity norm of a times x. Does that make sense? Such that the absolute value of maybe xj is less than or equal to 1 for all j. You guys see that these two problems are equivalent? This is, notice that like this stubby equal sign here. This is where I've plugged in the definition of the infinity norm. Yeah. I saw a hand go up and then go back down. Are we good so far? Okay. So, right. So one thing that we can do, just to continue to not think too hard, like, and by the way, on your homework, I was encouraging people in your office hours to do something very similar. When I see a product like this, it's like the ith element of ax, it may be useful to just go ahead and write out that full like matrix vector product formula. But let's do that. By the way, unfortunately, the indices on the board don't match the indices on my note, which is like danger zone when it comes to me making a mistake. So I'm gonna count on you guys to make sure that we don't do that. Okay, so we got the. By the way, I'm gonna stop writing the constraint on x for now. Okay, so we're just all going to agree that the elements of x are less than 1, greater than -1. Okay, so this is the absolute value of the sum over j of a I j x j. You see that? Subject to the constraint here. Everybody agree this is the ith element of ax? Okay. So let's actually just upper bound our formula for now. Okay, and then we'll go back and show that our bound is achieved. Okay, so how can we upper bound? We have the absolute value of a sum, so like what's like screaming at us for how to upper bound this thing? This is a triangle inequality, right? So this is less than or equal to, maybe I'll wrap around the board again, the max over x of the sum over j of a I j x j, like that. Right, so here I distributed the absolute value through the sum here, yeah, and that's what incurred this less than or equal to. Okay, well now we're in good shape because what is this thing? This is upper bounded by 1, right? So notice that this is upper bounded. Oh, oops, this is the max over x and I forgot to copy that. This is upper bounded by the max over I of the sum over j, a I j, absolute value, which is exactly the value that we wanted to compute. Yeah? So far, we've shown almost what we wanted to show on the screen, right? We've shown that the infinity norm is less than or equal to the quantity that we've written here. Yeah? Any ideas for like a strategy for showing that it's actually equal? Yeah. Yeah. So if I in general, when I want to compute a max, if I substitute in an x, then the max is at least as large as the expression evaluated at that x. Yeah. So any idea what x I should choose? Like this expression kind of gives me a hint, right? Which is that like I want the absolute value of aij, right? So at the end of the day, I would suggest taking xj to be equal to, and notice. If I wanted to, I could put the max on the outside of the x. Either order is okay. I can say that xj is equal to the sine of a I j, like that, which is essentially just engineering this absolute value here. And if I do that, then what we can check is that this will actually realize that max. Okay? Cool. All right, so good. So we verified this formula. And the good news is that these two formulas are ones that we can actually compute, right? Like if we know how to add, subtract, multiply, and divide, we can compute these norms. But we can't really compute the induced 2 norm of a matrix. Now the reason we took that little detour is that I'm going to try and write down a formula for the condition number of a matrix and a linear system. And it's going to involve matrix norms, right? And in fact, we're going to need our matrix norm to be an induced matrix norm for the formula that we derive. But then the problem is that we couldn't actually evaluate it if we wanted to do it with the 2 norm, right? So it's important to remember that other norms are out there that we can actually compute. Yes? Yeah. Oh, that's a good question. Yeah, so here I'm thinking of it being the max over I of the max over x. Right? You can kind of swap those two maxes. So one thing you could do is kind of choose an I and then choose an x. Yeah. Okay. Cool. So before we get started computing the nasty formula, oh, and as a review, oops, from last time, we argued that all matrix norms are indeed equivalent. Does anybody remember the argument here? Bueller. Yeah. Okay, so remember, here's the space of all m by n matrices. And of course, this is the same up to unraveling as the space Rmn, right? So we have a norm on this space, right? So we can think of it as a norm on this space where you just first reshape it into a matrix and then you compute the norm, right? It's a weird norm on this space where like different entries are treated differently, but that's perfectly fine. Yeah. Okay. Cool. So our real goal in life is to compute, it's my goal in life, and it's now your goal in life too, is to compute condition numbers for solving linear systems of equations. And our goal is to do that by kind of saying, like, we perturb A and B, and we want to know how much x changes. And then we're going to reshuffle that formula into a really tidy form and show that by looking at the norms of A and B, we can kind of predict how sensitive our linear system is. At least we can upper bound it. We're not going to prove a hard bound today, although I believe in practice actually it gets pretty close. Okay, so here's how we're going to do it. Is we're going to say, like, okay, if I perturb A by delta A and B by delta B, then how much does x change? That's the problem we want to solve. And as with most things when we argue about condition numbers, we only care about like kind of a limit as epsilon goes to 0. Just in some local neighborhood of A and B, how much does changing A and B affect stuff? Everybody with me so far on our goal? I think it's pretty concrete. Okay. So relative to what we did in the textbook, I'm actually going to flip the discussion a little bit backward, and I'm going to prove like a little lemma first here, which is the following. Then, so suppose that like our favorite matrix norm here is induced from a vector norm. Okay, so we have a vector norm. We've lifted it to matrices using this trick we've done so far. Then we're going to write down two very useful inequalities that we're going to use to help us in our quest to understand this formula here. Here's the first one. So then for all vectors v, we can write the following. So let's say that I take the norm of a times v, like that. This is a vector norm, yeah? Okay, so I'm going to do something really profound here. This is equal to, and by the way, we'll say norm of v is not equal to 0, because all the things we're going to write down are going to be really trivial for zeros. So when vectors are not equal to 0, they have norms. And so hence, I can do the following. I can say I'm going to multiply and divide by the norm of v. So this is equal to the norm of v times the norm of a v over norm v. Like that. So I just divided and multiplied by the same number. Okay. Now why would I do that? What is the length of this thing? What happens when I take a vector and I divide it by its norm? I know you know the answer to this. I know. What's its length? 1. Thank you. Right. So this thing has length 1. And remember, what is the norm of A? It's the sup over all vectors of length 1 of this product. So in particular, since it's the sup, we know that this is less than or equal to the induced norm of A times the norm of V. Okay? So essentially all it's saying is that I can take a matrix vector product and I can kind of split it into the induced norm and the norm of the vector. and that incurs an inequality here. So this kind of looks like Cauchy-Schwarz. It's like kind of similar. That make sense? Okay. Similarly, what happens if we have two matrices and we compute the norm of A times B? Well, remember that this, by definition, is the max over X with norm equal to 1 of A, B, X, like that, just by definition. And now it starts to look like this expression here, right? So for example, if I parenthesize it like that, right, then this expression is less than or equal to the max over X, the norm of A times the norm of BX, like that, right? So this is a constant. I can move it out there. And what is this? It's the max over X of the norm of BX. This is precisely the norm of B. Do you see that? So this expression is just equal to the norm of A times the norm of B. Cool? So essentially, we've shown a formula that I'm betting if I just wrote it on the board, like in the middle of our proof, you guys wouldn't think about it and you'd agree with me. But it is important to double check that this is actually true. And this is where we're using the fact that our norm is induced. Right? Obviously, we needed that in our proof, which is that if I have matrix vector product, I can incur an inequality and then multiply their norms. And similarly, if I have a matrix product, I can do the same thing. Any questions so far? These are just like handy fun facts. You guys look so engaged and excited for this calculation. Okay, so, yeah.
Wait, I haven't even thought this through all the way. Why would this fail with the F norm thing that Frobenius norm?
The Frobenius norm? It might not, but you have to check that it's true.
Okay, well, but it's not induced. But this,
yeah, so the Frobenius norm, at least the way that we defined it, is not induced, right? We didn't write it as the max of the norm or something. Yeah. Yeah, I think a fun challenge is to prove or disprove is Frobenius norm. Can it be understood as an induced 2 norm? It's not obvious to me. Yeah. My guess would be no, but I have to think through. Okay. So, right, our next task is to do some calculus. Okay? So we're going to do a little bit of computation here. If I were a more engaging instructor, do you remember that old, what was that? There was like a high school movie in like 2006 or so with the song with like you plus me equals us, something calculus. Okay. Right, so I have A plus epsilon delta A times X. I'm just going to copy the formula here because I want to kind of talk about it, make sure we understand what it is that we're doing. So, here's, I want to make sure that you understand that we are making a quick assumption here too, that like if you were a math student, you really should double check, but we're going to be a little sloppy here. So in particular, remember our goal is to figure out as we perturb A and B, and in particular now, we don't just perturb A arbitrarily, we choose a direction where we're going to perturb it, like delta A, right? And our question is like, how does this affect our solution? So here's the way to think about it. Now, we're going to fix a bunch of things. We're going to fix A, delta A, B, and delta B. And there's a scalar quantity, epsilon, which is the amount that we perturb, okay? And then we're going to think of the dependent variable as being x, right? Like as I change the matrix on the right-hand side, x has to kind of change to continue satisfying the system of equations, right? So that's why I've written x of epsilon. Like x here we're thinking of as a function of epsilon. That make sense? So here's where we're going to make a slight assumption, but this turns out to be kosher, which is that like for all we know, this is like a fractal or some like wild function. Like, it's pretty clear here that x should be a differentiable function of epsilon, but we haven't actually justified that, right? Because we're about to take derivative of both sides. I don't think it's worth arguing that carefully. Okay. In fact, there are probably cases where it's not, like if A is singular, but whatever. Okay. So let's differentiate both sides. Okay, so this is, and by the way, a different way of putting this is like this is an implicit definition of x, right? Okay, so if we take d over d epsilon, what's going to happen on the left-hand side? Well, we got the product rule, right? So we have the derivative of this times that plus this times the derivative of that. Yeah. So in particular, we're going to have so the derivative is delta A times x of epsilon plus the other way around. So A plus epsilon delta A times x, we'll just say prime is derivative with respect to epsilon here. Okay? And this, what is the derivative of the right-hand side with respect to B? This one's easy. Just delta B. Thank you. Okay. Everybody agree with this expression so far? And remember that we only really care about perturbations away from A and B. So it makes sense to just substitute in epsilon equals 0, right? Like we just care about, like, perturbatively as we move along from X, along from A and B, what happens to X. So in particular, we substitute in epsilon equals 0, we get this nice expression. So delta A times x of 0, which, what is x of 0, by the way? It's just A inverse times B, right? Like this is the solution that you actually wanted. Okay, so we have delta A times x of 0 plus, now we have A plus epsilon delta A. So this is 0, so it goes away. So I have A times x prime of 0 is equal to delta B, like that. Okay? Or we can solve, remember at the end of the day, we're really trying to figure out how x changes, so it probably makes sense to isolate this variable here. So, we have x prime of 0 is equal to, yeah, so if we multiply both sides by A inverse here, right, so we have A inverse delta B minus delta A x prime of 0. Sorry, I'm being slow. Delta A times x of 0. What did I made a mistake here somewhere. Delta A x of 0 plus A equals delta B. X prime of 0 is A inverse delta B minus A inverse delta A x of 0. Okay. Is that right? For some reason, I feel like there shouldn't be an A inverse here, so I'm just like quadruple checking so we don't get too far. Chris, help me out. Wake up. Oh no. Yeah, this is correct. I think I just made a mistake in my notes. That's all. Okay. All right, folks. So does everybody see that this is actually just directly saying, like, as I change A and B, this is this like kind of puzzling formula for what happens to X. Right, that's what's going on here. Okay, all right. So what we really care about is some notion of relative error, and this is where our calculation is going to get even hairier, which is why I keep like type checking and trying to make sure my answer is right. I really don't want this to drift away. In fact, if one of you people with a laptop cracks open the book, you can find this and to make sure I haven't made a mistake. Okay, so right, what we really want is the relative error of x. So in particular, I think a notion of error here is x of epsilon minus x of 0, all this divided by x of 0. Right, so this is the relative error of x as I perturb. Okay. Now, if I plug in a Taylor series for x of epsilon, right, then what is it equal to? So this is, you know, x of epsilon is equal to x of 0 plus epsilon x prime of 0 plus O of epsilon squared, like that. Right, so I'm going to plug that in here. And these guys are going to cancel, so I get epsilon x prime of 0 plus O of epsilon squared, all that by x of 0. Okay. Cool. So unfortunately for us, we have to plug this thing in. This is no fun. Okay. So what is this expression equal to? Well, this is an epsilon times A inverse, which I'm going to factor out of these two terms. My notes were missing a parenthesis before, which is why I was panicking. And so this is A inverse delta B minus delta A times x of 0, like that, plus big O of epsilon squared, all of that over x of 0. Okay. I promise we're not going to do too many condition number calculations in this class, but it's important for your health to do at least one in a course like this. Okay, so right, so what is this quantity, by the way? This is the relative error as I perturb x in this delta A, delta B direction. Okay, I'm going to erase this little Taylor series line here so I can keep writing. Okay, so now, now we've got some painful stuff to do. So we can apply the triangle inequality to kind of split off this epsilon term just so we don't have to keep writing it over and over again. Right? So this is less than or equal to the norm of these two things added together. So that's going to be kind of convenient. We're going to factor out this guy and this x is 0. Okay? So we have, this is less than or equal to the absolute value of epsilon divided by the norm of x is 0. All of this multiplied by, and now we're similarly going to use the triangle inequality to split off these two terms. So we have A inverse times delta B, and then a delta A x of 0. Cool? So this is the norm A inverse delta B. And then we've got a second term, which is the norm of A inverse delta A x of 0, like that. Yeah, all that plus O of epsilon squared. Everybody with me so far? So essentially all I did is I took the three parts of this thing and I just split them over the norm. Okay. So now, any suggestions actually? What's where should I go from here? If I'm like trying to make a nice looking bound. I think it's easy to kind of agree with the professor doing this calculation in front of class and like think like, okay, but if I were Gauss or Cholesky or whoever it was that derived this thing, like how did they do it? What was that? Yeah, we can take a limit possibly, but like notice that like it's kind of clear what the limit's going to do at this point because we've isolated epsilon, right? So you're right, like we definitely are going to have to do that. But in particular, like if we're like kind of programmed to just recognize like one small bound after another, notice like I conveniently gave you two formulas that we proved a minute ago that have to do with expressions that look like that, right? Yeah. Yeah, Axel's absolutely right. Like what is this thing? Well, this part is less than or equal to the norm of A inverse times the norm of delta B. And similarly, this thing, do I want to split it into three terms? Yeah. Yeah, I do. Okay, so this is less than or equal to the norm of A inverse times the norm of delta A times the norm of x of 0. Like that, okay? So here this is just applying the little lemma that we proved. Cool? All right, so let's reshuffle our expression a little bit. Notice, conveniently, we have a norm of A inverse now in both of these terms, so it makes sense to factor it out. So we're going to do the following. I'm going to say this is less than or equal to the absolute value of epsilon times the norm of A inverse. And I'm actually going to distribute in here the 1 over the norm of x0 for fun. And we're going to see that, like, essentially what I'm doing right now is just trying to massage this expression into something that's nicer looking, right? And it's hard to do. I mean, this is an annoying calculation. So we've got delta B over the norm of A. Why is that? Times the norm of x0, 0. Plus, we've got the norm of delta A, like that, plus order epsilon squared. Okay, that's not quite what I thought I was aiming for, so let me double check that this is right. So we have the inverse. Mm-hmm. Yeah, that's what I'm asking too. What was that? What was that? Yeah, that's yeah, I think it's Oh, I remember why. I'm sorry. Let's factor out also. So this times that times the norm of A. There we go. Like that. Okay, now we're good. Thanks, guys. Wow, this is fascinating. See, this is the same reason why your homeworks have small typos in them. Like, apparently, I sit there and carefully hand copy and spend time preparing your lecture, dutifully copy it into my notes, but incorrectly, and then can't see it. Okay, so now we all agree. I'm sorry that this is sitting underneath, but it's the product of these three terms times these three things. And notice that we're like starting to get somewhere good, because look at this term here. This looks like relative error, right? This is like the norm of the change at A relative to the norm at A. Right? Now we're cooking with gas. Everybody agree with me? You should. Okay, but unfortunately for us, it would be really nice here if we had the norm of B, but we don't. Right? So what are we to do? Well, remember that the norm of A x of 0 is less than or equal to the norm of A times the norm of, the norm of A, norm of x of 0, right? This is the same inequality just proved once again, right? So what happens when we take the reciprocal of an expression? You can see I'm sweating a little bit because I'm nervous. I can get it wrong. So if I take the reciprocal, the inequality flips, right? So notice we have 1 over the norm of A times the norm of A of 0. So this is upper bounded by 1 over the norm of AX 0. Yeah? And what is this? What is this product? Remember, AX equals B. Yeah? That's our whole thing here. So this is just the norm of B. Okay? So in other words, we're out of space on the board. So we're gonna, I was gonna be lazy and start doing that thing that I hate that math professors do where they start erasing things and like substituting terms in. But rather than doing that, I will take the time to copy. Okay, especially because we already did one sloppy thing. Well, I'm only permitted 1 per line. Okay. All right, so in other words, what we have justified is the following expression, that this thing is less than or equal to absolute value of epsilon, norm of A inverse, norm of A. We got a norm of delta B divided by the norm of B. We've got a norm of delta A divided by the norm of A plus order epsilon squared. Ta-da! Okay, so now we're doing pretty good. Okay, so now we're just going to give these things these names. Okay, I can stop sweating now because this is the expression I was hoping to get. Okay, so first of all, epsilon doesn't really matter here, right? Like we're just taking a limit like for small epsilon, and this is sort of to first order the change in our error, right? So the good news is there's no 0th order term, right? Otherwise we'd be really concerned. Okay, we're going to give this thing a name. We're going to call it K, kappa. This thing, we're going to give it a name. We're going to call it D. Okay, so what is D? Well, remember the independent and dependent variables, right? The independent variables are like A and B, and the dependent variable is X. So this is the relative error of the input, right? This is saying as I mess up A and B, the D is measuring how much they're messed up. Does that make sense? Okay. Well, so then remember our goal here, right, is if we change the input, how much does the output change? And if you remember all the way back to the beginning of our chain of inequalities here, the people on that refuse to come to class and watch on YouTube are going to have to just remember. Remember our goal was to bound the relative error of X, which is the relative error of the output. So you notice what happened? We have the relative error of the input on the right-hand side, the relative area of the output on the left-hand side. And these things differ, okay, by epsilon, which I could fold into the deltas if I wanted to take a limit. Yeah? But the more important term is this K. So, and what do you think K stands for? Think about like a spelling mistake. A different spelling mistake, but you're like right church, wrong pew. Condition number, that's right, because K is exactly, do you see that? It's the ratio between the forward and the backward error, at least an upper bound of it, yeah? So this is the condition number. Or really, sometimes we call this the relative condition number because we computed relative errors here, yeah? Okay, so in other words, this thing is really epsilon K D. plus big O of epsilon squared. Okay? So just the way to think about it is like the condition number is predicting that ratio. D is just is just the change in input. So it sort of like depends on your problem, right? But K does not depend on the deltas, right? It only depends on A. So now let's step back 100 feet and kind of figure out how to interpret this thing, right? Like we just went to all of this work to bound this thing. Why the heck did we do that? Okay? So first of all, let's say that I have small k. Right? So in other words, the right-hand side of this expression is very small, right? Well, what that means is that x is stable to changes in A and B, right? I see your hand there. I'm going to finish the sentence, then I'll call you. So is this a well-conditioned or a poor-conditioned problem? This is just sanity check. Like small condition number, is that good or bad? Good, right? Because the thing that I can measure, when that thing is small, I'm even more confident that the original solution is good. That make sense? Okay. For large kappa, in a sense, because we've only proven an inequality, we actually can't say whether or not our problem is well-conditioned or not. It turns out this is actually a pretty tight bound, so when you have a large kappa, you can also kind of conclude that this is an ill-conditioned problem. But that's a little outside of the scope that we've done today. Axel.
So it's a little weird that sort of A is in the term, like I guess like some property of A, like in this case, sort of relative error.
Mm-hmm.
Is in the term, but it's also in the case term. Like why do we call certain but it might be in the term?
Oh, that's a fantastic question. In fact, I would almost phrase your question slightly differently. So Axel has made a brilliant observation, which is if we look at these two terms, one thing we might notice, remember our problem was specified in terms of A and B, and in some sense delta A and delta B, right? By the way, like this is a conservative bound in the sense that like we haven't looked at the direction of delta A or delta B. Like it could be perturbing in some directions, it's pretty stable, and other directions not. This is actually definitely the case. Like think about identity matrix, like adding a diagonal to that probably doesn't mess with it very much. But in any event, Axel makes an interesting observation here, which is D depends on what? It depends on A, B, delta A, and delta B. That's because D is just like the total relative error of everything, right? In some sense, I've done a lame thing, which is just combine their error into one giant expression, okay? But kappa here depends on what? Just A. That's it, right? So first of all, would it make sense for kappa to depend on any of the delta variables? Probably not, right? Because we just want to look at AX equals B and kind of say, is it stable to perturbation, not this perturbation, right? So if my condition number depended on what direction I perturbed in, then it would be a very specific condition number. It wouldn't be a very general object, right? But there's a different question, which I think is hiding here. I'm rephrasing Axel's question because I think you started to ask the other way around, but I'm going to ask the forward direction, which is, why is there no B, right? Which is actually super surprising. Yeah, so what this is saying, at least if you believe that these inequalities are tight, is that to first order, the thing that affects stability of your linear system is just A. And in some sense, that actually makes a lot of sense, because what makes your linear solver probably problematic is like division, like inverting a matrix. And that's A, that has nothing to do with B. Yeah? And so that's sort of what's being expressed here. Yeah? So at the end of the day, the condition number is the product of the norm of A and the norm of A inverse. The other question that you guys might be asking is like, well, wait a second, isn't that number just 1 because like somehow you have an A and an A inverse? The answer is absolutely not. That's not how norms work. So the norm of A inverse is not equal to 1 over the norm of A. Okay? But yeah, you're absolutely right. So in fact, we can ask kind of extreme questions like where is the norm of A very well conditioned, where is it ill conditioned? In our next lecture, when we talk about QR factorization, we're going to talk about the best condition case, which is where this is equal to 1. So for example, if I use the 2 norm here, right, then that would mean that kind of all of my singular values equal to 1. And that would be a rotation, right? So it sort of is saying that the easiest linear system to solve is one that just kind of rotates the coordinate axis, which makes good sense, right? So let's write a few alternative expressions for this thing, depending on how we work with it. So right, so we did this expression on the board. Thankfully, after the smoke cleared and all of my terrible handwriting and math mistakes, we have proven the formula that is in the book and on the slides. If it's written 3 times, it can't be wrong, which is totally false because your instructor copy-pastes from one to the other. And essentially, what we've shown is that the condition number of a matrix, and remember, this is condition number specifically for solving linear systems of equations, right? This is not the condition number of the eigenvalue problem, for example, which I think is a common point of confusion because, like, people talk about, like, the matrix being well conditioned, but you can't really say that. It's conditioned for solving AX equals B. Is this value here. And that comes from this inequality that we've shown, that essentially the relative error of x is upper bounded by the relative error in your input variables times this condition number kappa. Okay? Incidentally, if I take A and I multiply it by like 75, what happens to the condition number? Yeah, so this is a good sanity check. So again, remember that kappa is equal to the norm of A times the norm of A inverse, like that. And it is the case that if I scale a matrix, it's the same as, and then take its norm, it's the same as taking the norm and then scaling, right? So in particular, this is equal to the norm of CA, maybe we'll assume C is positive just because I'm lazy, times the norm 1 over CA inverse, like that, right? Which is equal to CA times the norm of CA inverse, like that, right? So what did I just justify? If I scale my matrix, does the condition number change? Like, this is the condition number of the scaled guy. This is the condition number of the original one. So no, scaling doesn't affect condition number. This is a great sanity check. You see that? Because again, like, here is the condition. Do you see that this is CA and CA inverse is what we showed here. So this is exactly kappa of CA. And we showed that it's actually equal to kappa of A. So this is maybe a little bit counterintuitive at first, because somehow it feels like scaling a matrix up might make linear system easier or harder to solve. But that's actually not true. It kind of depends on like the ratio of like the biggest stretch to the smallest stretch. That's like what's more important here. And that makes sense, because if you think about solving a linear system, it's sort of like changing coordinates, right? And sort of the really unstable changes of coordinates aren't just like rotation or even scaling. It's the ones where you're kind of unsquashing one coordinate and leaving another one alone. Yeah, so that's sort of geometrically what's going on. Okay. So, yeah, so that's a thing that's worth checking, what we just did, is that this is actually invariant to scaling A, unlike the determinant, by the way, which is another common misconception. Condition number and determinant are not the same numbers. And by the way, for the identity matrix is equal to 1, yeah, which you better hope so, right? I mean, like, that's a very easy matrix to invert as they go. Okay, so there are so many different ways to write down condition numbers. Here's another one that I think is kind of a nice one. So in particular, you have condition number of A, and then you have of A inverse, or rather the norm of A and the norm of A inverse, right? And so one thing that you can check, at least for the 2 norm, I think there should be subscripts on this slide, right? Is that if I want to find the, what's the right way to put this? That the max over X with 2 norm equal to 1 of the norm A inverse of X, right? This is the 2 norm of A inverse, right? Which is one of the terms in the condition number, right? This is equal to 1 over the min over the same set of x's of the norm of AX. This is like not entirely surprising, right? I'll let you check this thing at home. And so because of this fact, we can think of the condition number as sort of this ratio of the biggest stretch of a vector to the smallest stretch of a vector. Does that make sense? That's essentially what this expression is showing.
This on the web.
Oh, Alexa agrees, or whatever this is, Siri. Right, so in other words, like a condition number, if I think of A like a quadratic form, like I look at X transpose AX, right, I can write the level sets of this thing, right? Then the ill-conditioned ones are the ones whose level sets are kind of like super lengthy, like that, okay? Whereas if you have circular level sets, those are the ones that are a problem. right? And that's because the ratio of this distance to that one is very, or I guess the other way around is very, very large. Okay? So lots of nice ways to understand this. So that sort of concludes our story about linear systems of equations. We now know how to solve them, when we should solve them, some places where they appear. Yeah? As a final note, there's a total chicken and egg problem here, which is that we've written down this condition number. Notice inside of the condition number is an A inverse. That's a problem, right? Because let's say that I solve a linear system and then I say, okay, can you please compute the condition number to make sure that I'm confident in my solution? Can I do that? No, because if I could do that, then like I would have solved A x equals B with high confidence, right? So somehow like there's a total chicken and egg problem here. This is a big issue, and so typically like computing this norm is just not possible. So in a sense, like you might say, okay, well Justin, like we just spent the last like what hour deriving a totally useless formula, and of course I tend to disagree with that, but it is absolutely right that if you have a piece of code for computing condition number, like you shouldn't trust it. Because it's only as good, like the condition number of computing the condition number is roughly the same as the conditioning of the matrix itself. That's a little bit fishy, yeah? That said, yeah, so like in particular, like what you don't want is like, well, what's the condition number of computing this thing? Or you're like, you know, what's the condition number of computing the conditioning of computing condition numbers? I mean, you could do this all day long, yeah? Basically, anytime you do a computation on a computer, it is subject to error, and that includes bounding the error of another computation, yeah? So of course, what we tend to do is to bound this condition number above and below. And we use like different conservative formulas, just like we did in this derivation here, to kind of show that like either the problem is at least this difficult or at most this difficult, right? Like that's what bounds are showing us. And luckily for us, there's actually some pretty reasonable ways that we can do such a thing, right? So in particular, here's some useful inequalities. One thing we might do is, for example, from the inequality that we proved earlier in lecture, we know that like the norm of A inverse times X is a lower bound for the norm of A inverse times the norm of X. So like maybe I solve my linear system and then I compute this thing. And at the very least, this is an efficient algorithm for upper bounding the condition number. But of course, again, I'm still kind of trusting this norm to make sure that you know, like if I had some weird catastrophic cancellation, you could imagine this number being unreliable. Yeah. So anyway, this is just a warning. You have to be so careful when you do this stuff. A different strategy sometimes people will use is they will compute, they'll solve the linear system, and then when they bound the condition number, they'll like use a higher precision in their number system or something like that, so that like the error here is probably lower than the error in the original thing. But these are like the kind of finicky things you really have to worry about when you do this computation. Okay, with that, I promise this is, I think, the last condition number we will compute for several weeks in this class, which is good because you can see it makes me uncomfortable too. I hate doing this kind of stuff. Okay, so I think with that, maybe we'll call it for today. So I'll hang out for the rest of the lecture slot since we've got the room anyway, and I can help you guys with your homework. And this way, we'll start next time with QR decomposition, which is the scheduled next topic for this course because we moved a little fast to start with. Okay, so again, to review, so far we've got matrix inversion, LU factorization, Cholesky for positive definite, and now we know how to kind of evaluate when things are well conditioned or not. That's sort of the complete story for linear systems of equations, at least in the sort of intro level. Okay. All right, so reminder, your homework is due this evening sometime, whenever it is on Canvas, 11:59. I'm sorry we did that. We're going to post a quiz, and we will give you some extra time to take it because we once again forgot to write it. I'm sorry, that's my fault. And their next homework is there. At the very least, please try to run the starter code. Just like make sure that it works in Python because it does require a library or two. And we posted some tips on the Piazza for like instructions on installing the software if you need it. Cool. So with that, I will hang out. And or if you're done with your homework or you don't feel like hanging out, I'll see you next time.